because all we wanted that n average as a function of you should diverge so that for every z you have a corresponding z, right? I mean, if you have this situation, this kind of situation, you are fine, right? Because then the ensemble equivalence will hold for any density. Okay. If it is this situation, then the average cannot be bigger than n star. Cannot be bigger than n star. No, if you have a conserved system, of course you have some number of particles. That is, whatever you fix, whatever you put, those are there. So now it is macroscopic distribution. Macroscopic distribution cannot be more than n star. Okay. So if you put a density which is bigger than n star, so now I will come back here. Okay. So now this alpha greater than 2 is just that. Okay. So alpha greater than 2, you have a finite density. Okay. Rho c. Okay. So if you have in a system, if you have density more than rho c, and if it is alpha is less than 2, then you are bound to hit something, right? I mean, you cannot accommodate all the particles macroscopically, right? I mean, no, macroscopic density cannot be rho star. And then what you have is that the maximum whatever is allowed will be distributed in the system, like rho star will be distributed, macroscopically. The rest, rho minus rho star times L, rho minus rho star, rho minus rho c times L. These are the number of or volume if it is a different. So this is the particle which will condensate. This particle, these many particles which could not be distributed macroscopically will find some site. Okay. Okay. So what is the meaning of macroscopically? Which means that they can be placed somewhere, but the total number of sites where they will be placed is not proportional to length itself. Right? I mean, if 100 sites they distribute themselves in 3, it is not that in 10,000 it will be, in 1,000 it will be 30. It's not, this kind of proportion should not happen. I mean, there will some finite number of sites or some sublinear sites they will, put themselves. Okay, I will not give you a proof, but in this situation, in this particular situation, in long time, t goes to infinity in GRP, they actually, accumulate one site. That is, you can show that, which I will not go there. Okay. So we should also, this one also has a consequence. So what is, right? I mean, in nature there are many places we see power laws. Okay. So for example, fractals, we say that if you take a distribution of coastline lengths or some, in different scales, you find there are power laws and rainfall, and there are many places power laws. So the power laws. So if you have a natural power law, so I'm just giving you a hint. I'm just saying that in a natural power law, it has to be greater than 2 or more. Okay. Why? Because whatever quantity you are measuring, it's a finite system. Whatever system you are measuring, it has some density, some average. Okay. That's, whatever you are measuring, it has some average. If you are measuring rainfall, average rainfall over 5 years, some number. I mean, you have some finite number, right? I mean, or average earthquake scale in Richter scale over 100 years is a number. Okay. So you have a finite average. So if you have a power law which is less than this, the average will be infinity. You don't have a control. Okay. But if it is greater than 2, what you can have is that you can have a finite average. So if it is more than 2, I'm just saying, if it is less than 2, then the less than 2 has to cut somewhere to make the finite average, because so the tail of a power law, right? I mean, cannot be 3 by 2, right? I mean, it has to cut somewhere with exponential. So if you are seeing a power law, probably it is more than 2. Okay. Reasonable. Otherwise, I will not say power law. It's not asymptotic power law. It cannot be. Okay. So that's something you have to keep in mind.
Can I just make one comment for the class?
Yeah.
Because we have discussed this and the addition of variables, and use a slightly different notation which may confuse. And that we assume that the power law is 1 over n raised to 1 plus alpha in our discussion. That's why 2 for pk translates to 1 in our case, and it's for alpha less than 1 we used to say that the mean does not exist. It's the same as alpha equal to 2.
Achha, okay. Okay.
So don't get confused.
Okay. Okay, so this alpha is not that alpha, so it's one difference. Yeah, okay, okay.
So one question, I understand this, but why this? Okay, I did not follow the logic that, okay, I can have processes in nature where the mean does not exist.
Yes, but I'm just saying that, you know, the one which you find, the examples which I gave in these situations, like, you know, if there is a finite average, that's what I'm saying. If you have rainfall or whatever, power flow in rainfall, power flow in stock markets, power flow you observe in all of them are more than 2. Okay, I mean, this is a fact. No, you have to find me in one example. But I'm just saying that if it is possible. Then, you know, if you have one, but I don't know one, then usually you have a finite average, right?
Can I suggest one?
Yeah.
Areas of river basins follow 4/3 law. It's known as somebody's law. And the Takayasu analysis explains this. But anyway, you just leave it at that.
No, all I'm saying is I understand this.
No, but
But
the finite, no, I'm just saying, in that case, the finite average is finite, and to have an average which is finite, you must be cutting up it somewhere, because the river basin size. Yeah. So that is all I'm saying is that. So that you can have 3/2, it is not a problem. I'm just saying that it's not asymptotic. Asymptotic is an exponential in there. It's e to the, right, I mean, it's 4/3 with e to the power some minus r by xi. That's it. It cannot continue forever. A power law with e to the power, that is not, you know, you have a finite average. This is not.
I mean, the number of river basins is finite.
Finite, yeah. So I'm just saying that if it is 3/2, it has to be cut somewhere. That's it. To make it finite. Yeah. Okay. No, if you, right, I mean, I'm not saying that this, if you call this is a power law, it is fine. I'm talking of asymptotic power law, which is asymptotically, it is rather exponential, not a power law. I'm just, because the tail is a power, it's not a power law, it's exponential. Okay. Okay, I think this one I erase. And now I talk a little bit about this pairwise balance again, okay, just to make certain statement. So in the pairwise balance, which you have seen is that you have a configuration C, where you have some K site, some site which is occupation K, and N and M. Okay, 3, and some 3 sites. And in a construction of this pairwise balance, what we say is that when a particle goes from here to here, okay, that one is balances by a particle which is, by a transition which is from here to here. This one balancing that. Okay. So the point is, right? I mean, this is the way. Yeah. Okay. So this is the balance which we're trying to make. So from here to here, it is balanced. Okay. So now it is not, right, I mean, in the construction, it is not, so here, right, I mean, in the rate, what you have, you said that particle go from here to the neighbor, and that's the reason you were constructing, this also exists, just from the previous neighbor to this one, this transition also exists, right, a forward transition. So now, if you change the dynamics, instead of first site, let us say that the 5th site. Question that will it work? Well, it will work. Only thing is that you just have to, that 5th side to this is balances by, so this red one from 5th side to this balances by the 5th side to that. Okay? That's the way it will balance. So it is this K and M, doesn't matter where they are. As long as you have prescription for every site, there is, it can come, uniquely can, there are many other ones. For every transition here, if you can balance with any other transition, then it is okay. Okay? So this will work for, wherever the particles are. So that means that it is it will be true even in 2 dimensions. Right? If it is a 2-dimensional system, there are particles and boxes take a particle, put in a neighbor which is in 45 degrees, right? In the next nearest neighbor or wherever you put, okay? Because if you go back previously, you also have one unique configuration from where particles can come here and go there, okay? So the K can be anywhere in the lattice, so it is true for 1D, 2D, 3D, okay? Okay, or any other lattice which is compact, like, otherwise, so one where it may not work is, for example, here you go like that, that's on a tree. So where you can go here, but that is a very ill-defined problem here, because if particle can go somewhere and it cannot, right, you would just go here and here and here, and from here you have to define what to do, like, you have to say from here to here, or something you have to say, okay? So basically, all I'm saying is that this site has a incoming arrow, but the outgoing arrow is not well defined, right? In this kind of situations, it will not work. And as I say, that the minimum thing for this kind of pairwise balance to work, minimum, that it's not guaranteed, but the necessary thing is that every configuration has as many inward arrows as that many outward arrows, so that you balance one with the other. You can choose one with the other, and that choosing can be many different ways, right? You choose differently, I choose differently, so there can be two different pairwise balance conditions. Okay, so that comes from the fact that you see the master equation has a lot of positive terms and a lot of negative terms. Okay, so the general situation that 1 plus 3 plus 5 is okay, 3, okay, I don't know, 6 plus 2 plus 1. Okay, so that balances, but that doesn't have to be this equal to that, that equal to that. It doesn't work, right? Equilibrium is a situation where there is exactly one here, same numbers appear here, right? From here to here is same as here to here, okay? But in non-equilibrium, you can have 3, 1, 3, 5, and you still have somewhere there is a 5. It may not be here. This is 5, 3 plus 5 plus 1. So you are smartly choosing this 5 with that 5, this 3 with that 3, this one with that one, like that, uniquely. So inward arrow, outward arrow should be same, and it is possible that there are many 5. Okay, so in these situations, it's a choice, like which you have a different construction which will balance, but the procedure has to be clean. That's the point, and this tells you that the dynamics also works for any dimension. So GRP, this whatever I wrote down, this is true for any dimension. Okay.
Each such choice would give you a different state.
No, same stationary state is the same. Right? Because this, all you want is a stationary state, this should balance with that. How? And it is your construction that who is balancing with whom. This is an extra statement. This is not a physical, right? There are a lot of transitions which are happening, and you are trying to, actually smartly trying to find out what balances with what, so that it satisfies the steady state master equation, NP equal to 0. And if you can find one, it's a fine. So if you can find one, even in a great step, like the whole the problem is solved. Okay, and then this is a huge. It's a great utility, right? I will not discuss all them, but it's.
So the choice of C double prime is not uniquely prescribed, but it's 1-to-1.
1-to-1.
So given set of C to C primes, that has to be unique in that sense. I think PK wrote unique, but it's not a unique choice. But you can't have to use the same C double prime choice.
Some prescription which within this prescription this is unique, but you can have a different prescription.
Exactly.
Okay, this is exactly the one, right? You can have this is there are a lot of terms which are some numbers you want to balance. And it should be exhaustive. It has to be exhaustive. It has to be for all configurations. That's.
Given this choice, you uniquely give this P of C.
Yes, P. Yeah, stationary. Okay. So this is true for any dimension. So this is another thing which I added to the previous discussion. I forgot what I else. Okay. It works in any dimension. Okay, okay. So now let us say that here the particles are going only forward. Let us say that you also add, which is a choice, so that you add something here. Say that it can like this. Okay. So let us say you make a choice that you take a particle and probability P. With an extra parameter you introduce, it goes to left. The rate is un. So going to right is just p times that. Going to left is 1 minus p times un. U of n. Okay. So I just modify this. Okay. So you decide right where to go. Rate is this, and with this this additional one. Okay. So now question that will this thing work? Right. So what? Right. Think of this, in terms of this pairwise balance, right? This is very nice. Yeah. So think of in terms of pairwise balance, right? So what you are saying is that both arrows which balances each other, like this versus that, these are in the same direction, right? So instead of u, if you have pu, that p both sides cancels, like because these are in the same direction, right? This rate is p times u, and this rate is p times u. So at forward transition, transition is balancing by a forward transition. A backward transition can balance by a backward transition because the P is same, so it will also work. Okay. So if you have this situation, this will also work. Okay. Symmetric or asymmetric or completely asymmetric, whatever you do, this model will work. Okay. So this is a very nice model, solvable, exactly solvable model in non-equilibrium thing. Okay. Yes, you have a current. Oh, let us, okay. So the next thing we do is current. Okay. So that's very nice because it's a non-equilibrium one. We have to also find what is current. Okay. So can we find the current?
But naively it looks symmetric if P is half, right? I mean,
but with, so P, if P equal to half, no.
There is
no current.
Okay.
P equal to half, there is no current. Yeah. In generally, I mean, I was just talking about this model. Right.
In general, there is a current.
There is a current. Yeah, P equal to, so P equal to 1, okay, P equal to half, there is no current. P equal to half, there is no current. But let us find the current, okay? It's simple, so we'll do that. Just 2 minutes. So, along with this, in the pairwise balance, which I erased now, we also get a condition. From the first condition, we get that this Fn minus 1, Fn equal to Fn minus 1 divided by U. That's the equation which you iterated to get this equation, right? I mean, equation that Fn equal to this, right? I mean, F0 after putting F0 equal to 1. Okay, there was an equation like that. So this equation has a meaning. Okay, so let us use this equation firstly to calculate current. So let us calculate current. Current in this model, right? I mean, let us say that P equal to just 1. So this side is not there. Okay, and then we can generalize for any P. Right? P equal to 1. So P equal to 1, which we did earlier. So the current is that whenever particle transfer from this, right? I mean, this is the transition. So UN, right? I mean, UN. So this is the if you have some particle n here. So the rate at which particle is going from here to here is just UN. Okay. So UN average has to be current, right? I mean, that's the way particles are moving. So UN average is the current. So now what is UN average? Okay. So just because by now you know that it looks like a single site product thing in grand canonical ensemble. So basically you can say that this is just UN Fn, like the probability which I write here, Fn z to the power n divided by Fz, summation over n. Okay, I'm using just this probability that your n particle here, and then you are moving to right. Probability that your n particle here, this divided by that, and rate at which moving is un. So that gives me current. So that un Fn equal to just Fn minus 1. So this term can be replaced by Fn minus 1. Fn minus 1 times z to the power n, but I put n minus 1, I put a z here and summation over here, Fz. Okay. So now this one is just Fz. Okay. This is just Fz. If you replace the variables, the first term is not there, so it's basically Fz. So this part goes, and this is just z. Okay. So the current in the system is just z. Okay. Z is the fugacity. Okay. So now let us say that I want to plot current versus density. Okay. What is the current versus J versus rho in this situation? Okay. So what kind of function do you expect? Goes down. Why? Completely full.
But there can be
there is nothing called completely full here. Yeah. Okay. So this bound is anywhere, right? It will go all the way. Okay. So no. I mean, so where to search, right? Even if you are searching, where to search? Because current is Z. Now I am trying to plot as a function of rho. So there must be a relation between Z and rho. So do you remember how rho depends on Z? That is a general one, no? That is a general statement, right? So if you have any conserved quantity and the corresponding fugacity, when you increase fugacity, that quantity increase. That's a pretty general statement. Okay, because I argue, right? Because of this curve, if you remember, I'm just reminding you, because some function qn, and then you are.
Yeah, I forgot. They actually said the camera is just stuck on this board, so just use this board.
Okay.
So erase that and try.
Okay. Okay, anyway, so last time I also talked about some function, and this is just fn or qn or whatever, and z to the power n will bring it down, and larger the z, you have more area here. So the corresponding density will also increase, because you are accessing more. If you increase z, you access more, more in terms of the value of the conserved quantity. Okay, you will access sectors where the value of the conserved quantity is larger. Okay, you will access more and more such things. So the average will go up. Okay, so that's the point. So when you increase temperature, see this conserved quantity, again I am to repeat. So there are always conjugates for the conserved quantity, E and T and magnetic field and H and volume and pressure. So these are the kind of, you can put, right, what are the other one? N and mu. So mu means e to the power beta mu. So if you put corresponding fugacity z here, e to the power beta you call it z, e to the power h you call it h, whatever you call it. So these, with respect to this variable, when you say that this is z mu, let us say z mu, zt, zh, zp. So if you increase zp, m has to increase. There is no option. That's the one which I'm saying. So if you increase temperature, actually you are accessing more and more larger and larger energies. So that's the point. So this is an increasing function. So rho is an increasing function of z. That's the general statement. Rho is an increasing function of z. Okay. So now z is also in the same way, this same graph, right? It's same increase. So that's basically rho equal to 0 to 0. It's some increasing function. The details depends on the model and what is u and all kind of thing, but this is what it is, right? And so if you increase density, it will increase. Okay.
But suppose there's a condensate form, then
Ah.
suppose it cannot
Saturate.
Yeah, it saturates. Yeah.
then it becomes flat.
Yes, flat basically meaning like that.
Actually, it's the other way around. It's not other way meaning, yeah.
Like that.
I believe so. Because yesterday you plotted rho versus z.
It's like that. Okay. Yeah.
Turn that over.
Turn it over. Yeah. Geode versus rho is the other side. Yeah. Yeah.
There has to be a singularity, at z equal to z, cos theta. So the first derivative has to be.
No, but this is the right.
The red one is what? J as a function of z.
Rho.
Rho. So the
Rho.
like this, no? And there has to be a singularity at z.
Not ZC. This is rho C. So at rho C, yeah, you say.
The slope will be.
So when it is condensate, it will go like that and probably ligament something like that. So this is rho is fixed there, right? Actually I cannot draw the.
This is also similar to the graph of z for BC, right? Because
Yeah, it's the same thing.
There has to be a
Yeah. Yeah, when it is condensating. Yeah, if the rho goes all the way to infinity, then there is, right? If there is a condensate, then you have a singularity. Okay.
So, the partition function is fz to the power n. We're taking the probability. Why is there?
No, because this fz to the power n is just fz times fz times fz. So each one corresponds to one side. So it's like, right? It's just a product measure. It's a product measure. So this kind of state, okay. So this is, let us name it now. So this kind of state, when it is a product of thing, it's called product measure. Okay. Okay, there is also a lot of interesting stuff about the dynamics, which I will not do today. I will do rather some other things. Oh, so this one is not allowed. Okay, non-allowed zones. So I will now erase this part. I think this one I will not. need. I'm missing out something, but I'm just don't. If I remember, I will come back again. Okay, so I will now say that some utility of this kind of system. So what you right? I mean, you did this is exactly solvable model, but where else you can utilize? Like so what? Right? I mean, what can you do with it? So let us see. So there is a. So now I am going to talk about this connection of this mapping to exclusion processes. Okay. Okay. So like you ask a question saying that the number of particles something. So those are processes where exclusion processes where each site can occupy at most one particle. Okay. So can we do something about I don't know, can we do, right? This is the information mapping. So I just want to give you information about this mapping. Okay. So now let us see that you have a system which is a particle, let us say 3 particles, and then there is a box vacant, there is 1 particle, and there is some no particle, there are 2 particles, like that. Okay. Or maybe 2 particles, some boxes are like that. Okay. So what you can do, what you can do is that so you can identify the particles as 1. Okay. And the box as 0. Okay. So some way. So what you say is that this one, you think of this, you are writing it like that. So it is as if you are writing it like that, and then these particles, 3 particles, and then there is a box, and there is 1 particle, and there is a box. There is a box with 2 particles. Right? I mean, so the one boxes are like that. You are considering it like this. So what will happen is that now this model will become. So this to that will become just this one. You can identify 1 or 0 because there are 2 symbols now. Okay, so you can identify 1 or 0. So so this is just because I want to call it also particles now. I can call it a particle here 1 1 1 and 0. This box is 0 and there is 1 particle. This is 0 and this is again 0 and this is 1 1. Okay, so configuration wise, each configuration in a zero range process can be mapped to a configuration in exclusion process, right? I mean, this is in this system, each site can have at most 1 particle, right? I mean, in this system there is only 1 particle. Here the density can be infinity. In this system, if you call the number of ones in this one, this will be not infinity because at each site you have some number of particles. There is a relation between them. We can find the relation also. So if you have m boxes, okay, I think I use L boxes, so I call L boxes with m particles, n particles. So that will map to a system with L plus n is L tilde. It's a the system size is L v. Let me call it a notation V now. Okay, V. So V equal to L plus n in this system, and then number of particles is remain number of particles, right? I mean, this is number of particles. So why the density will be finite here? Because now you have to divide n divided by L plus n. Okay. So if the density here, which is rho, right? I mean rho, which is n divided by L, if this is rho, then here the density is rho tilde equal to n divided by L plus n, which is rho divided by 1 plus rho. Just divide. Okay. So that's the density. Okay. So all this is fine configuration wise, but can you map the dynamics now? Okay. So the dynamics, which is here, what is the dynamics here? The dynamics here is that the particle. So let us take one step in the dynamics. So let us say this particle goes here. Okay. So the new configuration is the 2 and 1. So let us write that. Huh? No, divide by L, divide by L, divide by L. So you have so Okay, so let us say this particle goes here. Okay, so what is the new configuration? So if this goes here, then you have a box with 2 particles. So that means that this configuration will go to box with 2 particles. Okay, and then a box with another 2 particles, a box with 2 particles, and the rest is what it is, like 0, 0, 1, 1. Okay, so now let us look at what is the change has happened. Like so here this particle actually goes here, right? I mean, so this particle moves forward. So this particle goes right. I mean, this 1, 0 is exchanged, right? I mean, so this is there. This is there, this is same as that, this one is exchanged. So this 1, 0 goes to 0, 1. So this is exchanged. Okay. So this particle goes here. But what is the rate? Rate is u of n, u of 3. Right? I mean, this particle goes here, the rate is u of 3. So what is the new model now? So you have an exclusion, okay. So you have an exclusion process. So you have an exclusion process. Exclusion process is the one where each side can take only at most 1 particle, so 1 or 0. So you have an exclusion process. What is the dynamics? The dynamics is that particle move forward with a rate which depends on the size of the domain. Okay, so you have a lot of 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, like that. And what is the dynamics is that the particle moves from here. Right, I mean, this particle can move forward with a rate depending on how many ones are here. Right, I mean, so what I call domain is that the consecutive things, like this is one consecutive thing, one domain and separated by 0. This is one domain, and let me put another 0 here. This is one domain, and this is no particles, no particles. So this is one domain, 0 size, and this is one domain. So these are the domain. So here 0 particles means things cannot move, and here, right, I mean, the rate depends on from if this particle wants to move forward, it will go with rate u of 4. This is also u of 4. Okay, accidentally everything is u of 4. This is u of 5. Okay. So that's the rate. So this is the new. This is the exclusion process. So for this exclusion process also you have that solution, right? So for this exclusion process, you have the same solution. So now question is that, the solution tells you that distribution of block sizes. It will not tell you the particle. So for example, here there was no correlation, right? I mean, this one is, I mean, except that there is a conservation. How many particles are here? How many particles are here? They are not correlated enough because because of this product measure, because you just separate out, and you could actually write it's a product of something. So here there is not correlation, but here the particles are correlated, right? I mean, so when you say condensation, what kind of things will happen here? So you have a large block, okay? So this one will call a phase separation, because it's like 1 and 0, like 1 and 0 can be 2 different things, which ones are separating out completely, right? I mean, and a large block of ones, basically a macroscopic block of ones, that's a phase separated state. It's like 2 different liquid coexisting. If you call 0 and 1, this is kind of 2 different, they're separating out, like liquid, like oil water or something, like if you put oil water and mix and they separate out, like it's, so that's the kind of thing happening. Now this transition, which we will call condensation transition, will now translate to phase separation transition. Okay, so now we want to employ, this is the phase separation transition, and now let us say that from zero range process we also learned one other thing, which you have that if you take in zero range process un, okay, this is also I forgot to mention, I will mention it on the way. I'm not very systematic. So un, some function. So we say that un can be expanded in the Taylor series. Let us say that it is expandable in Taylor series. Then you have 1 plus b by n with up to some constant. So constant I'm dropping out. B by n plus c by n square, something like that. So what gives you condensation transition is that when b is greater than 2. Okay, so this is like alpha, because you look at this function which we take n by n plus it is actually n plus 1 by 1 plus 1 by n to the power alpha to the first term is that 1 plus alpha by n. Okay, it's still a decreasing function, by the way. It's a decreasing function going to a constant. No, that's not, I was giving a wrong. So this is still a decreasing function going to a constant, and this is alpha by n, alpha greater than 2, you have a transition. So if you have un, it will behave like that, and then you can have a transition, right? I mean, b greater than 2, you have a transition. So any function where, if you Taylor expand, the first coefficient, Taylor expand around n equal to infinity, the first coefficient will tell you whether there will have a transition or not. It's a very strong statement, right? The model is somewhere, and it's a statement. Okay. So similarly, let us say that it is not expandable like that. Okay. So then the term is that you still want to go to a constant. So let us say 1 plus b by a by n to the power sigma. Right? I mean, you do not know. If it is not, then it will probably behave something like that. Okay. So in this situation, which I am not proving, just making a statement, so just for you to know. So a by n to the power sigma, sigma less than 1, you have a transition again. Okay. So now general is that un is 1 plus, in the first term is a by n to the power sigma. When sigma less than 1, you have a condensation transition. If sigma equal to 1, you have to look at what is the coefficient of sigma equal to 1. Okay. If it is greater than 2, you still have a transition. Okay. So these are the criteria of condensation transition in zero range process. Okay. So similarly, the same criteria can be used here. Okay. So now what you say un is like particle transfers here, right? So particle transfer, as you know, un, I also show that un is related to the current. When the particle goes like that, average un is current. Okay. So now I am not talking about directly mapping of GRP to here. Okay. So what you can think is that you have a system, some system, right? I mean, ones and zeros, and then what you have is that you have some which is, if it is ones and zeros, you can always. Oh, sorry. Oh, okay. 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 No, but I keep okay. Yeah, natural to go to the other side. Yeah. Okay. It was saying, okay, okay, I'll go there. So now I will not talk about this. I will erase all that. I think it's not needed. So you think of any system, like some system with 0 and 1, and then a system with 0 to 1, you can always it is always in terms of blocks, right? Some ones and zeros and some ones and zeros. So it's like 0 ones. And then maybe another one, another block of 1, maybe all zeros, I do not know, something like that, some blocks. So now the current, the U is actually the current, right? I mean, I may not have exact mapping, the dynamics may not be same as that it depends only on the size of the block. The dynamics may not be that particle moves with a rate depending on the size of the block. Okay, it can be any other dynamics. I did not know, but let us say that I measure current. Okay, so if I measure current, then the current will be some like J, which is current of a block of size, current across a block of size K. Let us say. Okay, if the block size is K, I say that current in a block of size K. So that is J infinity, okay, size n, why k, n is J infinity times 1 plus b by n plus something, right? I mean, so if the block size is n, the current across this block, let us say that you can measure. Okay, so if this is the behavior, then you know that this is interpreted as that. So you expect the transition to occur when this first coefficient is greater than 2. Okay, so. No. Steady state. So, for example, you did not know. I mean, I'm just saying you did not know pairwise valence. Let us say they have not. I'm just saying that if you listen, right, as Mohanty has pointed out. So, the solution of the problem first time when it was introduced was already known. It's not that pairwise balance gives you a steady state. So this is one way you can see the steady state. It's not that if you do not know pairwise balance, it is possible in a system that there is a pairwise balance, you are not able to find it. You still have a steady state.
No, that is true, but a system can have a steady state by not satisfying pairwise balance.
Yes.
Then do these statements remain true?
No, that statement may not be true for other reasons, but not for this reason.
This is more to do with this model, not the way you saw it.
Yeah.
Not the way you found the steady state.
Yeah.
Because I was just a bit confused about this word of how universal this is.
Yeah. So basically, right, that's a very, very nice question, right? I think if you know, the equilibrium can be restated, saying that statistical mechanics of detail balance. Models satisfying detail balance, right? So you can also ask a primary, right? One simple question is that what is the statistical mechanics of systems which satisfy detail balance? Okay, it's a good question. We do not know, right? I was just which has pairwise balance.
Okay. No, you just said detail.
Sorry. So statistical mechanics of systems which satisfy pairwise balance. It would be good to it's good to construct, but it's good to write. Yeah. No, you don't have, but it's a class still, right? Equilibrium is a class in the whole scenario. Equilibrium is a class of models, right? Which satisfy detail balance. There is a class of models also which satisfy. So now conditions, right? So the questions.
These conditions that you can just look at the term B by N, that was derived assuming there was some pairwise balance. No.
Property of the model.
Property of the model. GRP has.
Very good. Okay.
This has nothing to do with pairwise.
Pairwise balance to show, prove that these kind of steady state are the steady state. The factorized steady state is the steady state. I use pairwise balance to prove that.
Okay, but if I think of some other model, then this might not be
true. Yeah.
Actually, the same steady state will also be there if you have detail balance.
Can I tell you one other comment? For example, if I'm erasing half of it, so if you think of the model, let us say that P and 1 minus P and P equal to half, the one you're talking about. So you can construct a detail balance, you can also construct a pairwise balance. So I'm just saying that, for the same steady state, you have two different constructions, both of them will work, right? So, and it is possible to have many constructions which will work, right? In a given situation, it is only right. If you are, if you have a nice eye, you can actually look for what cancels with what, and it's finding. It's nothing. If you can find, it's fine. So, what is the difficulty in thinking of statistical mechanics of detail pairwise balance? Is the condition, right? You do not know what is the criteria on which pairwise balance will be satisfied, kind of thing. So that kind of criteria is not known for any other method, like matrix product or Bethan search or anything. So if it works, right?
But PK, do you know of any example where pairwise balance works, but the answer is not a product measure?
Yes.
You do.
Many.
So then,
Many.
So that makes it a little non-trivial, right?
No, many. This is pair factorized steady state. Sorry, not pair factorized state. It's called pair factorized state. Yeah, pair factorized state, cluster factorized state. This is all. There are a lot of works which are. So these are all kind of. You can pairwise balance satisfied. The best on that. So I have also a suspect that matrix product answers is somehow based on that intrinsically, right? You have to uncover it, but with matrices and some correlation has to be taken care. But it is just the simple idea of the pairwise balance is that locally you are balancing something, right? This one is balancing with that. So that is basically the point is that if this one balances with that, if you translate all over the lattice, you get this balance wherever you go, right? So I will not be able to do this matrix product very well. So I will just so there's a similar concept you use there, right? So somewhere it is hidden. It's a very nice one. I really many examples actually. I mean, people have not identified it. There are many other words which has not identified. They have solved the steady state some other way. But if you look very carefully, you say that, oh, come on, I mean, you just do pairwise balance, it is so simple. I mean, why the, right, I mean, but you have to find that. The point is that there is no method to construct a pairwise balance. You have to find something, like, you watch for something, Okay. So the point is that if in a system, if you can measure the current, okay, of a block, current passing through a block of size n, you measure that. And how does it change block size? Okay, if this is the situation, then b greater than 2, you expect a phase transition to happen, right? I mean, phase separation transition to happen. So that is one criteria. Okay. Other thing which I wanted to, other thing which I wanted to mention is, so this part is clear. So this is a criteria for obtaining phase separation transition in exclusion processes. Okay, so yeah, it can fail very badly if you have very strong correlations in the model between blocks. For example, if you have a long range system, but of course there is across a block there is a current, but this kind of, so basically, so there is with some salt. Okay. And then other thing I wanted to say is that when you go to this zero range process, the boxes are not correlated, right? I mean, but if you make a mapping from here to here, and then you put a un, which is, let us say, 1 plus 2 by n or 2.5 by n, that BC, this free particle BC, B2 by n. So if you take that, then this will phase separate. And when there is a phase separation, when this transition occurs, you have infinity correlation, right? I mean, you have a correlation length which is coming up there, right? I mean, so now the boxes are not correlated, but the particles here are correlated. So can you find correlation of these particles? Okay. So can you find the correlation of these particles? I think I will try a little bit, because I give you this idea of D and E, I try to construct, right? I mean, how using this D and E, you can find correlation in this problem. Okay. So that would be some way of justifying why I introduced D and E. But the statement which I made, that starting from a dynamics, getting DE, that procedure is a little longer. I do not know whether I will have that much of time, actually to cover that part. Okay, so I'll try to do for this kind of problems. Okay, so exactly zero range process. So you have a zero range process, you map it to exclusion process where the dynamics is that. Okay, dynamics is that particle move forward with a rate u of n, and is the size of the block where the particle resides. Okay, so that's the dynamics. In this dynamics, there is I want to find particle correlations. Okay, so I'll not do it in full, but I just want to construct a matrix formulation, and it's pretty simple. It's not enough barrier. Okay. Okay. So now, this one I think I can erase. Yes. So let us see that what we want. What is the thing we need? So in zero range process, we know the steady state solution, right? I mean, so basically, if you have a P of Ni, okay. If you have P of Ni, all P of Ni, that's given by product over I equal to 1 to L, F of Ni, and a delta function, times a delta function, which is for the summation over I Ni minus N. That's the thing. So this P of Ni, you are, instead of Ni, now your variables are different, right? Si. Right? I mean, so this one, but we will have a same probability. Okay, the probability will be same. So let us take one configuration, because this is a configurational probability. Let us take one configuration. So let us say that 3, 2, 0. These are the number of particles, 3, 2, 0, 1, something like that. So this will be 0, 1, 1, 1, 0, 1, 1, and this is 0. So 0, 0, 0, and 0 and no particle. So 0 and this is 0 and 1. Okay? So that's the construction. So probability of this, whatever rest, has to be same as probability of this. But what we want to write is that we want to write is a matrix product form, right? I mean, so if I write it is a D and E, D for this and E for that, then that will be dot dot dot. So this is same as P of E, D to the power 3, E, D to the power 2, E, E, D to the power, I do not know what. I mean, I will not, I mean, because this is not complete, so I do not know how many, at least D, at least now it's D, and then dot 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 dot. If whatever I put it later, okay? So that's the thing we get, okay? So now this one has to be same as that, okay? So now a simple way you can make it. Can you think of a simple way of making it? That this one has to be same as this one. So now what you can see is that 3 appears here. So if you take E is some kind of projector, which you do not know at this stage, you have to find out. But if you take E as a projector, then you can do it. For example, if you take E equal to some alpha and beta, like that. Some, I mean, I do not know the dimension of these vectors. I do not know anything. I'm just writing it. If you write that, then this one, if this is answers again, I do not know it will work. At this stage, it is answers. Okay, I do not know at this stage whether it will work. So this is just this is alpha, beta, d to the power 3, then alpha, beta, d to the power 2, alpha, beta, like that. It continues. So now you can see that this probability is now become just product of these numbers, right? I mean, this is just product of this times that times that. So this one now can be identified. If you, of course, in this probability, this is also there, but that is anyway there. So this one has to be identified of f of 3, right? You know, p of 3, 3. So this is this equal to f of, so dot 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 dot. This is f of 3, f of 2, f of 0, f of 1, f of something, like, you know. So this is this probability from zero range process. We know that this is f of 3, and with delta function, something like that. Okay. So now, if you identify this with that, then you are done, right? So beta d to the power 3 alpha equal to f3. Then of course in the same definition tell you that this one is f2, this one is then next one is e, again this beta alpha beta. So this beta alpha is whatever, this is f0, this is f2, like that, right? This is pretty clear. So what you get is that, so this one will tell you that beta and d to the power n alpha equal to fn. Okay, that's all you need. So now beta d to the power n alpha equal to n, and this one, because f0 is generally you have taken to be 1, then beta alpha you can take it to be 1. If you don't take it, it's also fine, but you can take beta alpha, this dot product, these two vectors. So this is a number, this has to be 1. Okay, so this is f0. This same definition goes here. So now can you construct? So right now, you know, if you can you think of a matrix D which actually satisfies this equation. So if you do that, then your all D's and E's are known, and once D's and E's are known, any correlation function you can calculate using these matrices. Okay, so let us try to find out what exactly D and E can be. No, I mean, no, right, I mean, no, E is, so E square should be? So that will happen, right? I mean, if I take alpha, beta alpha equal to 1, that will happen. No, no. Alpha, let us put it alpha beta, alpha beta. Okay. So if alpha beta equal to 1, then this is still E. This is E square. I am writing E square. This is E, this is E. So that means this is E square. And if I put this is 1, then this is again E. Now I don't need anything. So call it something else. I don't need it. Whatever I write, that's what it is. Is it not called a projector?
Well, maybe it's not called a projector.
Yeah, okay. So the name is, there is a misnomer. So you call it something else. Okay. So outer product of two vectors, alpha and beta. So I construct outer product of two vectors, alpha and beta, as E, and put it here. Okay. So that is, projector is a bad name. Okay. So, but if that is the definition of projector, it satisfies. Like if E square equal to E is the definition of projector, it still satisfies. Okay. Yeah. Okay. So beta d to the power n is Fn. So now question that, can you construct this? Okay. No, I think this is not something. Again, this is searching. So I don't know. Right. I'm not expecting an answer. So what you can do is that you write alpha is just this one. Let us say 1, F1, F2. So this is my alpha. It's an infinity vector. Alpha equal to F1, F2, F3. This is the vector. Okay. You take alpha to be this vector, and D to this raising operator, the one which raises. Right. If you take D, raising is a dagger. Okay. So if you take D to be a raising operator, then operating on alpha will just give you, just push the whole vector to upward, right? Just if you have so basically if you take D equal to 0, 1, right? Everything is 0, of including diagonal and off diagonal, everything is 0, but off diagonals are 1, and everything is 0. Just above the diagonal it is 1. So then what will happen is that this 0, first one will become F1. So multiply this matrix, right? This one multiplied by 1, F1, F2, like that. If you multiply this, so this will be just F1, F2, like that. You just push the vector up. That's raising. Okay. So this is you know that this is also equivalent to a dagger. Okay. So if you take D to be that one and beta, so once you raise, you have to pick up this. Right? Once you raise, you want, so basically D to the power n will, so if it is a raising operator, it will raise this vector n times. So you get on the top Fn. And beta, if you take 1, 0, 0, 0, it will just pick up that. Okay? So if you take beta equal to just call 1. 1 means 1, 0, 0, 0, 0, 0, 0, like that. And D equal to this vector, then D to the power n will just each time it just raise it. So that D to the power n, the first coefficient, first one will just Fn plus 1. This is right. I'm just saying this is beta as a vector, and D to the power n of alpha. So this is just Fn plus 1, Fn plus 2, like that. Okay. So now if you put beta D to the power n alpha, you just get Fn. Okay. So it's a pretty simple construction, right? So you know beta, and just because you already know Fn, so you can just put it here. So you have your D and E, and once you have D and E, all the equation which I wrote will work now. Okay, so the correlation function, everything you can calculate right then. Only thing is that this matrix is now infinity, right? You have to be a little careful.
Is alpha times alpha dot beta is equal to 1 satisfied?
Yeah.
1 plus.
Yeah.
Oh,
Yeah. So again, right? If that is the definition, it still works. Okay, F0 is 1. So right, that is F0. Alpha times beta is just F0, right? Alpha, right? So okay. So now if you have questions, yeah. Am I missing anything else in GRP to be mentioned? Yeah, okay. So basically, so this D and E we constructed here, and now I will change to a different problem. Okay.
same paper that defined the exclusion processes.
Spitzer, yeah.
Spitzer. So that's a remarkable paper and sort of started a field.
Okay.
I forget when it was, I mean, 60s, 1960s.
16, yeah.
60s.
Yeah.
1960s.
So, no, I mean, no, yeah. There is a translation available probably.
No, it's written in English. Spitzer used to be at Cornell. Spitzer. Frank Spitzer.
Yeah, okay.
No, this.
No, this one yeah, okay. Anyway. Now the original paper I've never read this actually. Spitzer's original paper. Yeah. Some people, yeah. Okay. Okay, let me try a little bit of constructing this DE for different matrices, right? So now what I'm trying to do is that I go change it to another model, okay, in non-equilibrium systems, okay, and then try to see, if I can use the same methods like D and E which I constructed, that kind of things can I use it, and that's the one I will try. So the model is, so you have a, so this is the one example which I gave in the first lecture, okay. So you have, let us say, one-way traffic with vehicles and things like that. So the vehicles are like 1 and 0, these are the same 1 and 0, and the dynamics in the system is just 1 0 going to 0 1, okay. And then now let us, and there are many particles, and this is also, you have a lattice, okay, lattice site I, and there are many particles in this system, so the total number of particles is n, and then it's also a ring. I will also take a periodic boundary condition, okay, for the time being. Okay, I have a periodic boundary condition, and then there are many particles, total number of particles is n, and if particles just go forward, if there is a vacancy with some rate, just because there is only dynamics, the rate can be, can be 1, that's your time scale, okay. So you can put the rate to be 1. So now this is again a simple case, because if there is only only this is the dynamics, then this is again simple, right? All configurations will be equally likely because it's homogeneous, and even though particle moves forward, they will cover, they just go round and down. So the probability measure is pretty simple here, okay. Why I'm doing this, that the probability, this measure will be very complicated once you make this periodic boundary condition to open boundary, like if you make it open of length L and enter rates with alpha and exit rate is beta. Once you make that, it becomes pretty complicated, okay. So let us try with the periodic one first, because the dynamics of the bulk remain the same. So we try to find out how this dynamics, right, what you say that 1 0 goes to 0 1, how does it translate to this DE, okay, if I have a state, and that's what I want to do, okay. So what you have is that you have a configuration here. So the configuration can be thought like not thought. The configurations can be like the configurations. I'm writing it SI. Okay, SI is equal to now 0 and 1. Okay, so this is my configuration. So probability of this is my configuration, and probability of configuration I want to represent. 1 by D, eventually 1 by D, and 0 by E. So that's what I want to represent. So so then probability of a configuration, I want to write as a product state, right? That's also pretty general. So probability of the configuration, probability of configuration SI. So this equal to product, right? Product over matrices. Instead of writing matrices, I can, of course DE, but this configuration I do not know, so I can call it SI times D plus 1 minus SI times E. Okay, if I make this product, because if SI is 1, then I get D, and if SI is 0, then I get E, because this will, so this one tells me that if it is 0 and 1, correspondingly I get D and E. So this is product over I. Okay, so this is my matrix It's a product of matrices correspond to this configuration, and then because it's periodic, I also want to take a trace like that. Okay. If it is open boundary condition, I have to put two vectors from both sides. Okay. So this is trace, and then I have trace of d to the power, because the sum will be summation of SI equal to 0 and 1, then this will be just d and e, right? I mean, this matrix is just d plus e, right? I mean, summation of SI equal to 0 and 1, that gives you all configuration. So d plus e whole to the power L. Okay, so that's the standard partition function which I know. So that's my probability. So now question is that what kind of dynamics or what kind of equations this d and e should satisfy. Okay. So now I have given these dynamics that 1 0 goes to 0 1. So for this I have a master equation, right? I mean, you can write a master equation dp by dt equal to mp. Okay. This is the master equation, and the master equation will contain all the terms were for every transition, right? I mean, all the terms are there. So and this is a 2 to the power L by 2 to the power L matrix. Okay. So now what I do is that a state I actually can write is just as if it is E, and then this is the master equation, and steady state implies that MP equal to 0. So I want to find these kind of equations. Okay. So this M, let us look at what is the matrix M, what the matrix M has. Okay. So what it has is that M can be written as something like, there are two sides. So every transition, every transition only involve two consecutive sides, right? I mean, every transition, because it just takes 1 0 to 0 1, so it will involve only two consecutive sides. So the matrix M can be written as some operators, which is H I plus 1 summation over I. Okay. So this is some operator. Okay. So what is the meaning of that? Each H, right? I mean, so basically this is sum of operators. So if you have a state like that, I plus 1, and so this operator will act only here. First one term will act here, next term will act next to, next one will next to, like that. Okay. So this is the operator. Okay. I do not know if I call the direct product is. So anyway, so this is the operator. It's fine with people, right? Okay. So now what I do is that at each site you have either D or E, right? I mean, that's the way you want to represent. Okay. So the total number of states can be written as just a direct product of ED. Okay, times ED. This is actually at I, this is at I plus 1, this is ED at I plus 2, like that. Okay. So this is like a state, like in the stationary state, the probabilities of each configuration you can get it from here, because this is E like that. This is also work like that, right? So everybody is familiar with the direct product. So this means it is E and D are already some matrices which I do not know, but E cross E. So this means E cross E just means that EE, ED, EDE, DD. So this is a 2 vector, and if you make a direct product, it will be 4 vector, right? And so this H, what you are acting here, what you are writing here, this is operating on is a 4 vector, which is operating on this, right? I mean, this is symbolic, but but these are matrices, right? This is 2 by 2 matrices in the situation which I talk about in Ising model. Let us say it's 2 by 2 matrices. Here I do not know some size of the matrices, but symbolically this is just this. It's right. I mean, this is the matrix. It's a 4 by.
D and E operators, or are they column vectors?
No, D and D matrices.
They matrices.
They are same matrices. What I start with, right? I mean, these matrices I know, but I am representing the stationary probability by these matrices. So what I am doing is that I start with a configuration. I see what my what M does to this configuration. Okay, so that's what I try to do, right? And I try to see that so I'm just saying that. Okay, All I want is that H operating on this should be 0. So MP to be 0. Okay? Are you getting this? So now question that if I make another direct product, that will be E, right? You know, one E will be there and next one D will be there. So there will be 8. So now by the time if you take L of them, you have all the weight of all configurations written everywhere. Each of them is a 2 by 2 matrix. If I take a trace, then you know for each of them I will get something, right? You know, get the corresponding weight of the configuration. Is it fine? If you are familiar with the direct product, then it is fine, right? You know, how many? No, I mean, no, because that will be futile. Right, you know, I don't. So how many people know or used direct product of matrices somewhere? Okay, yeah. For I think many would not. Many would not have. So I can let me just define.
Yeah, exactly. Just some
two matrices I define. What do you mean by a direct product? So let us say that you know you have a matrix A, B, C, D, and some matrix E, F, G, H. Okay. So this is the matrix, and you want to make a direct product of that. Okay. So basically this is equal to E times this matrix. Whatever, this matrix I call A and this I might call B. Okay, so this is EA, FA, GA, HA. Okay. So now this the dimension, if this is 2 by 2 dimension, here if you multiply, so now this will become A, B, C, D. So now multiply D, so that is AE, BE, CE, DE. And F, AF, BF, AF, B, where is B? BF, and GF, HF, like that. So this becomes a 4 by 4 matrix. Okay. So if you take a 2 by 2 matrix, multiply, it becomes a 4 by 4 matrix. So A, B, B, I think both ways it works.
Yeah, you have a choice.
You have a choice.
You can find an account of this in Person Wang's book. In one of the appendices, where he discusses second quantization also. Or maybe it's a separate appendix. But it's a nice account. Just read it.
Yeah, so both ways, right? I mean, otherwise it will not be bringing it to, right? You know, if this confusion is there, it doesn't matter. Yeah. Okay. Okay, so you know one way. So I mean, I'm just saying that consistently you use whatever, right? I mean, you know, it works this way or that way, right? I mean, you know, yeah.
You should stick to one way.
Stick to whatever. I stick to one way. Oh, in between, you know, that's not allowed. So stick to one way. So okay. So this is the direct product. Okay. So now if you do the vectors, for example, if you have AB, a vector cross another vector CD, then it will be A, or okay, in the same notation, it will be C times AB. D times, so this equal to C times AB and D times AB. So this becomes 4 by 4. So I'm saying that you know this is, I mean this is symbolically I'm writing, these elements are itself as a matrix, but it's still okay, right? I mean matrices within matrices would work. So if I make a direct product, I get like that. So why I'm doing this is that look at what this master equation to M times P does, right? So now if I write it in site wise, right, you know, if I write it as an operator which is acting on each site, then on each site whatever things can be done has to be covered. I mean, you know, I and I plus 1, whatever things has to be covered, the M has that part, right. So if you take a matrix M, so there some transition you are writing it here, C to C prime or something. So all the transitions which are from site I to this, that can be pushed to one place. All the transition from I plus 1 can be pushed to they can be pushed to some other place. Okay. So this one, the whole thing can be written into operators as if the transitions are happening, those which are happening at 1 to 2, those which are happening from 2 to 3, like that. So this is, and the 2 to 3 has all loss and gain terms, everything is there in M. So you have to take care of all of them, whatever happening at neighboring sites. Okay. So now we have not found what is H. We'll try to get what is H in this situation. Okay. So what I'm saying is that at each place I am writing a D and E. So basically this is just ED cross ED. So which is a vector like that. And for H, what I have to do is that I have to find what is happening on this side. So what is happening is that if it is 1 and it is 0, it just becomes 0, 1. If that is the case. So if I write in the same basis, let us say call it EE. Yeah, I mean, this E doesn't carry an index here because I'm thinking some two consecutive sides. As long as it is consecutive, it is true. So this is EE, ED, DE, and DD. Okay, and in this basis I have to write it. So EE, ED, DE, and DD. Okay. So now what is the transition which is happening? Who is losing? And so basically, so now what happens is that ED you gain, right? I mean, so when 1 0 goes to 0 1, so 0 1 will appear and 1 0 will lose, right? I mean, so 0 1 will appear here and 1 0 will lose. So this is DE will lose and with the expense of 1 0. 0 1 will appear and this will lose -1. DE going to DE and EE will nothing happen. So this is 0 0 0 0 and ED and EE there is no relation, these are 0 0. Okay. So all it does is that whenever it is so DE, that part is lost to make ED locally. Okay, that's your dynamics. So that part I am bringing from the master equation. So this one, if I multiply by that, has to be 0. So basically, if I have to make this one 0, if I can ensure that this acting on this is 0, then I ensure things. Okay. DE. This is the same master equation. Like you have 1 minus 1 has to be 0, right? I mean, this column sum has to be 0. So I am taking only the part where ED at some consecutive site has lost, right? I mean, ED and I am making, sorry, DE has lost because 1 0 becomes 0 1. So DE has lost and ED you gain. Okay, this is the part of the. No, this is not clear. No, this is okay. No, not that side. So, okay, I think. So one can write. I mean, so this one when I'm writing it, even in quantum mechanics, when you write things like that, what you mean is that when this operator is actually an operator where everywhere there is identity, and there is a H here, right? I mean, so this is basically 1 cross 1 cross somewhere at this HI plus 1, this HI. This is actually the operator, and you have sum of many such operators, right? I mean, one which is acting here, one which is acting there, and one which is acting there, and this sum is just a sum of all these operators, right? I mean, when you say that AI dagger AI this, so it means that this one is operating here, and you are saying that in the space it is everywhere. You can have an identity like I cross I cross I, right? I mean, when you say AI dagger AI plus 1. Summation over I. No, I don't know. I'm making sense with it. It makes sense to other people. It's a direct product of things, and then you can think the other places it is not acting, right? When you have one operator which is acting, taking particle from here to here, everywhere else it's the identity. Okay. So the next one which is acting here, you can say that everywhere is identity. It's acting only here. So it's a sum of all such things. So it's like a Hamiltonian, which is sum of these consecutive terms. I mean, I'm constructing what this matrix is. Okay, so this matrix is operating on this space because where I have written is D and E. Okay, so now what I have to make is that if this is MP has to be 0, then this matrix operating on this should be 0. So one simple thing is that just make everything is 0, right? I mean, that's not a solution. So you have to find out a solution to this equation. The equation basically H acting on ED cross ED equal to 0. If this satisfies, then you are done. Okay, so then you get the solution to the master equation. And in this case, H I have constructed this is H, because this is what is happening, like 1 0 going to 0 1, basically this one is DE is losing and ED is gaining. So that's the way I put it here. And then I think I'm crossing time, so we'll continue little bit in this direction. Okay, how to just multiply this and try to get an equation. So how to make this 0 without putting 0 directly here. Okay. The other way of making 0 is to make a sum which is 0. So you just shift it. So this itself is not 0, but it will produce a term which cancels with the next one. And if you do it over things, it will be 0. So that's the procedure. Okay. Okay. If you have questions. Yeah. No, that when I write the master equation, every rate appears once with positive signs, once with negative sign for some configurations, right? And it appears in a way that the column sum is 0, because it is it is created from the rows, and it goes into the it is created from the rows and goes into the columns, right? I mean, that's the way they're written. So if you have a term there, it goes there. So when you write the DE becomes ED, DE has lost that particular one, that part is lost, and ED has appeared, and the rate is 1. So that's the rate is 1. So if it is P, if the rate is P, you should write P. If this is P, then you should write P minus P. Okay, I think that is not a bad idea. Let us put it P and P and P. So then that is better. No, that is perfectly. So this is, I do not know, but it's still well defined. So you can say that each one, I mean, if you don't, right, I mean, so the dimension, so each one you can call it identity here. Everywhere you put identity, which is the same dimension of this one. That's the right, I mean, the same thing. But this works in matrix multiplication. This works. Okay.